The human brain runs on roughly 20 watts of power. That is the same amount of energy used by a dim incandescent light bulb. Meanwhile, the most powerful supercomputer ever built consumes tens of megawatts just to stay cool. That is a gap of roughly 1 million to 1. If the brain was simply a biological circuit board doing the same kind of computation as a silicon chip, that ratio would be physically impossible. You cannot run the same class of calculations on 1/1,000,000th of the energy budget. The math collapses. This means one of two things. Either we fundamentally misunderstand what computation is, or the brain is doing something else entirely, something that our computers are not designed to do. And the evidence increasingly points toward option 2. We have spent decades trying to simulate the human brain using conventional computers. The approach has always been the same: add more transistors, increase the clock speed, throw more memory at the problem, and hope the gap closes. It has not closed. In fact, the more precisely we try to model the brain, the more clearly we see how poorly matched the hardware is to the task. This is not a problem that faster silicon will solve, it is a problem of physics. The brain and the classical computer are operating according to different physical rules, and until we build machines that follow the same rules as biology, a true simulation of the mind will remain out of reach. But that is beginning to change. Let us start with the scale of what we are actually trying to copy, because most people underestimate it dramatically. The brain contains around 86 billion neurons. That number sounds enormous, and it is. But the neurons themselves are not where the complexity lives. The complexity lives in the connections between them. Each neuron is linked to thousands of others through structures called synapses. When you map the complete network of connections in a brain, what researchers call the connectome, you arrive at a number of approximately 100 trillion distinct synaptic connection points. 100 trillion. To put that in perspective, there are roughly 10 times more synaptic connections in a single human brain than there are stars in the Milky Way galaxy. And these connections are not static, they are constantly shifting. Every second, hundreds of trillions of synapses are either strengthening or weakening based on incoming chemical signals. The brain is not a fixed circuit. It is a living, reconfiguring network that never sits still. Simulating that level of dynamic, parallel activity on a machine that processes information sequentially is like trying to capture the ocean with a series of still photographs. You can approximate it, but you will always miss the motion. The most ambitious attempt to tackle this directly using classical hardware was the Blue Brain project, launched in 2005. The goal was to build a biologically detailed digital reconstruction of the mammalian brain from the ground up. The team at the École Polytechnique Fédérale de Lausanne used some of the most powerful supercomputers available at the time. After years of work, they succeeded in simulating a small neocortical column from a rat brain, just a sliver of tissue containing roughly 30,000 neurons. To run that simulation, they needed to track every ion channel, every electrical spike, and every chemical gradient across all 30,000 cells simultaneously. The computational cost was staggering, and that was for 30,000 neurons. A human brain has 86 billion. When researchers tried to project what it would take to scale that simulation up to a full human brain at the same level of biological detail, the numbers became effectively unreachable. You would need computational resources on the scale of a large industrial facility just to store the data, let alone process it in anything approaching real time. The classical approach had hit a wall that no amount of chip fabrication could dissolve. The problem became vivid in 2013. A team of researchers used Japan's K supercomputer, one of the most powerful machines on the planet at the time, to simulate just 1 second of brain activity. The simulation represented only about 1% of the full human brain. After the researchers fed in the model and started the calculation, the K computer needed 40 minutes of processing time to generate that single second of neural activity. 40 minutes of supercomputer time to recreate 1 second of biological thought. That is not a simulation. That is an extraordinarily slow motion replay of a system running thousands of times faster than the computer trying to capture it. More recent work has made genuine progress. In 2025, a team used the Fugaku supercomputer, which succeeded the K computer as Japan's flagship machine, to simulate the mouse cortex with nearly 10 million neurons and 26 billion synapses. They achieved performance that approached real time. This was a significant milestone, but it was made possible by simplifying the biological model and running it on hardware that cost billions of dollars to build. And even at that scale, The mouse cortex is a fraction of the complexity of a human brain. The gains in classical computing have been real. The ceiling is still not high enough. What makes this particularly difficult is not just the number of neurons, it is the architecture. A classical computer is fundamentally a linear machine. It processes information along a path. Data moves from storage to processor, gets calculated, and moves back. Even with parallelism, the underlying structure is flat. The brain is not flat. It is a three-dimensional, fully interconnected mesh where every part of the network can affect every other part simultaneously. Running a three-dimensional interconnected biological network on a two-dimensional linear architecture is the source of the bottleneck. We have reached the edges of what silicon can do. Now let us talk about the energy problem, because it reveals something much deeper than just efficiency. When you look at a modern supercomputer facility, most of what you are looking at is not computing. It is cooling. The machine generates so much waste heat that it requires industrial cooling towers and a continuous supply of water just to keep the processors from destroying themselves. These machines consume megawatts of electricity. The actual computation is a fraction of the total power budget. Most of the energy goes into fighting heat. The brain generates almost no waste heat. If you put your hand near a thinking human brain, you would not feel warmth radiating off it the way you would from a running processor. The brain solves complex problems, generates language, processes vision, coordinates movement, manages emotion, and runs the machinery of consciousness on a metabolic budget that your body sustains through a modest diet. 20 watts, continuously, for decades. This discrepancy is not just an engineering curiosity, it is a physical clue. In classical computing, heat is a fundamental byproduct of making decisions. When a processor switches a transistor from 0 to 1, it is physically forcing electrons through a resistive gate. That physical act generates friction. Friction generates heat. The more decisions you make, the more heat you produce. This relationship between computation and thermodynamics is described by something called Landauer's principle, proposed by physicist Rolf Landauer in 1961. The principle states that erasing a single bit of information requires a minimum amount of energy, and that energy must be released as heat. Every time a computer discards a possibility to reach a conclusion, it pays a thermodynamic price. You cannot get around this in classical computing. It is baked into the physics. But the brain does not seem to pay this price in the same way. It is not overcoming resistance to force binary decisions. It is computing in a way that bypasses the Landauer limit, or at least skirts it dramatically. One reason this might be possible is that quantum computation can, in theory, be reversible. A reversible computation leaves no information behind. It erases nothing, and if nothing is erased, no heat is generated. The brain does not achieve perfect reversibility, but its efficiency suggests it is operating closer to that regime than any silicon chip ever has. This points toward a different physical mechanism underneath the biology, and the most compelling candidate is quantum mechanics. For a long time, suggesting that the brain might operate on quantum principles was considered fringe science. The standard objection was simple and seemed decisive. Quantum states are extraordinarily fragile. To maintain quantum coherence, a system typically needs to be isolated from its environment, cooled to temperatures near absolute zero, and shielded from any external vibration or electromagnetic interference. The brain is warm, wet, chemically chaotic, and constantly bombarded with thermal noise. The assumption was that any quantum state inside a neuron would collapse within femtoseconds, far too fast to play any role in cognition. This argument seemed airtight. Then scientists started looking more carefully inside the neuron itself. For decades, neurons were understood primarily as signal cables. The outside membrane carried the electrical impulse. The interior was thought to be just plumbing. That picture has changed. The interior of a neuron is packed with a dense structural scaffold called microtubules. These are hollow cylindrical protein structures that form the skeleton of the cell. They are found throughout biology. In most cells, microtubules are pure scaffolding, but inside neurons, they may be doing something more. Physicist Roger Penrose and anesthesiologist Stuart Hameroff proposed a theory they called orchestrated objective reduction, or OR. They argued that microtubules are not merely structural supports. They suggested that the geometry of the protein chains forming the microtubule wall and the arrangement of electrons within those chains might create a partially insulated quantum environment inside the tube. If correct, This insulation would allow quantum states to persist long enough inside the neuron to participate in information processing. The microtubule would act as a biological quantum waveguide, shielding coherent quantum states from the thermal noise of the surrounding cellular environment. The scientific community was skeptical of this idea for years, and the skepticism was reasonable. Extraordinary claims require extraordinary evidence, but the evidence has been accumulating. Researchers have observed quantum vibrations in the protein lattice of microtubules. They have found that energy can propagate through these structures with anomalously low loss, behaving more like a coherent wave than a classical thermal disturbance. Studies have linked this propagation to networks of tryptophan molecules inside the tube. When these molecules resonate together, they appear to generate a macroscopic quantum state, similar in principle to how a laser works. In a laser, individual photons synchronize into a single coherent beam through a process called stimulated emission. Inside microtubules, molecular resonances may synchronize into a single coherent quantum state that spans the length of the tube. This is not proof that the brain runs on quantum mechanics, but it is no longer dismissible as fantasy, and it changes the conversation about simulation entirely. If there is quantum processing happening inside neurons, even at a limited scale, then a classical computer cannot faithfully replicate it. A binary switch cannot simulate a quantum superposition. These are not just different speeds of the same process, they are different physical categories. A simulation that ignores the quantum layer of the brain is not a simulation of the brain, it is an approximation of certain statistical behaviors that the brain produces, which is a very different thing. To understand how quantum computers offer a genuine solution, we need to understand what makes them fundamentally different. A classical bit is always either 0 or 1. It has no ambiguity. A quantum bit, called a qubit, can exist in a superposition of 0 and 1 simultaneously. This is not a metaphor. It is a physical reality. The qubit is genuinely in both states at once until it is measured. When you build a system of multiple qubits, they can also become entangled. Entanglement means that the state of one qubit is instantaneously correlated with the state of another, regardless of physical distance. The two qubits are no longer independent. They are a single unified quantum system. Measuring one instantly determines the state of the other. This is where the power of quantum computation comes from. When you solve a problem with classical bits, you explore possible solutions one at a time or in parallel batches, but always moving through discrete states. When you solve a problem with qubits in superposition, the machine is exploring all possible solutions simultaneously through quantum interference. The probability amplitudes of wrong answers cancel each other out, while the probability amplitudes of right answers reinforce each other. The computation does not guess and check. It converges on the answer through the physics of wave interference. For simulating physical systems like the brain, this matters in a specific and decisive way. To model any physical system, you need to describe its energy state. In physics, this description is called the Hamiltonian. The Hamiltonian is essentially the energy fingerprint of a system. It captures how every component of the system vibrates, interacts, and evolves over time. A single neuron has a Hamiltonian. A network of neurons has an incomprehensibly more complex one. If you can define the Hamiltonian accurately and simulate how it evolves, you have simulated the system. When a classical computer tries to simulate a Hamiltonian, it has to solve the mathematics explicitly. It computes the differential equations that describe the evolution of the energy state, one step at a time. As the system grows, the equations grow exponentially harder. At the scale of even a small neural circuit, the classical computer essentially freezes. It is trying to describe every ripple in a pond by tracking every water molecule individually. A quantum computer does not try to solve the equation. It tries to become the equation. This is the concept of quantum simulation. You configure the qubits so that they are governed by the same physical laws that govern the neurons. You set up the interactions between qubits to mirror the interactions between biological molecules. You are not calculating what the neuron will do. You are building a quantum replica of the neuron and observing what it does. The hardware and the simulation are the same thing. This idea goes back to Richard Feynman, who made it precisely in the early 1980s. He observed that nature is not classical, nature is quantum. Therefore, if you want to simulate nature, you need a quantum machine. For 40 years, that prescription sat waiting for hardware capable of fulfilling it. The practical bottleneck until recently was error. Qubits are extraordinarily sensitive to their environment. A stray magnetic field, a temperature fluctuation of a fraction of a degree, a cosmic ray passing through the chip, any of these can cause a qubit to flip from its correct state to an incorrect one. These are called quantum errors, and for years they accumulated faster than any algorithm could run. The computers were powerful in theory and unusable in practice. The field of quantum error correction existed to address this, but for most of its history it faced a cruel paradox. Adding more physical qubits to a system to implement error correction codes also added more potential failure points. The system became noisier as it grew larger. You were fixing errors at the bottom while introducing new ones at the top. This changed fundamentally in late 2024 with the announcement of Google's Willow quantum chip. Willow was not simply a faster quantum processor, it was a demonstration that the error correction paradox could be broken. The team at Google showed that by grouping physical qubits into logical qubits, clusters of physical qubits that collectively protect a single unit of quantum information, the error rate decreased exponentially as they added more physical qubits to each logical group. For the first time, making the system larger made it more stable rather than less. Adding more physical qubits exponentially reduced errors rather than amplifying them. This is the turning point. It is the proof of concept that quantum computers can, in principle, maintain stable quantum states for the duration of a complex computation. For biological simulation, this matters enormously. The brain maintains a continuous state of consciousness for decades. Simulating it requires a computer that can sustain coherent computation not for microseconds, but for minutes and eventually hours. The Willow results suggest that is achievable. We are moving into an era where quantum algorithms can run long enough to observe how a digital neural network evolves and adapts over time. We can feed the simulation time-dependent data and watch it respond. We are no longer limited to taking an instantaneous snapshot of a brain state. We can press play on the simulation. The immediate practical applications of this are in medicine, specifically in the understanding and treatment of neurodegenerative disease. Diseases like Alzheimer's, Parkinson's, and Huntington's are not simply diseases of neural death. They are, at their molecular foundation, diseases of geometry. The machinery of the nervous system relies on proteins, and proteins must fold into precise three-dimensional structures to function. A protein begins as a long chain of amino acids. To become active, this chain must collapse into a specific shape determined by the interactions between its chemical groups. If it folds correctly, it does its job. If it folds incorrectly, the misfolded protein can become toxic, clumping together into aggregates that damage and kill neurons over decades. The challenge of predicting how a protein will fold is one of the most computationally demanding problems in all of science. A modest-sized protein can theoretically adopt more distinct conformational shapes than there are atoms in the observable universe. A classical computer approaches this by guessing a shape, calculating the associated energy, adjusting, and guessing again. This brute force search is so slow that a supercomputer can take months to determine the structure of a single complex protein. The field changed dramatically when DeepMind released AlphaFold, an artificial intelligence system trained on known protein structures that could predict folding with remarkable accuracy. But AlphaFold is a pattern-matching engine. It works by learning from examples. For novel proteins with no structural analogs in the training data, it struggles. And for simulating how misfolding happens dynamically in real time under specific molecular conditions, it is not the right tool. A quantum simulation approaches protein folding from physics rather than pattern matching. In nature, a protein folds by seeking the configuration that minimizes its energy. The chain samples different shapes continuously and gravitates toward the state of lowest energy, the stable configuration. A quantum computer can simulate this process directly. The qubits settle into their own state of lowest energy automatically by the physics of quantum mechanics, mirroring the physical process the protein undergoes. The computer does not search through possibilities, it physically enacts the folding. This allows for dramatically faster identification of stable protein structures and, critically, for the simulation of how proteins misfold under specific genetic mutations or chemical environments. Combine this with the concept of a digital twin and the implications for medicine become concrete. Imagine scanning the molecular structure of a specific patient's brain, loading that data into a quantum processor tuned to reflect the patient's neural chemistry. You have now created a sandbox replica of that person's neurobiology. You can introduce a candidate drug molecule into the simulation and watch how it interacts with the misfolded proteins in real time. You can observe whether it interrupts the aggregation cascade. You can detect unexpected interactions with other molecular systems before the drug has ever entered a living body. You can run thousands of variants of the compound in a single afternoon. This compresses a development timeline that currently spans over a decade and costs billions of dollars into something measurable in weeks. It turns the first stage of drug discovery from a process of educated guessing into something closer to precise engineering. Beyond medicine, there is an application emerging in the field of brain-computer interfaces, and it involves a problem that has defined and limited the technology since it began: latency. When a person using a neuroprosthetic decides to move a hand, the brain generates a cascade of electrical signals that encode the intention. A classical computer receiving those signals must first filter the noise, then run a decoding algorithm to interpret the pattern, then generate a command, and finally send it to the motor. Each step takes time. The result is a noticeable delay between intention and action. The user does not feel like the prosthetic is part of their body. They feel like they are operating a tool with their thoughts, which is a fundamentally different and less intuitive experience. Neural signals are not clean binary messages. They are probabilistic clouds of electrical activity distributed across many neurons simultaneously, riding on a background of biological noise. A classical decoder must wait until the signal achieves sufficient statistical clarity before it can commit to an interpretation. It discards ambiguity because ambiguity breaks the logic of binary decision-making. This waiting is where the delay lives. A quantum processor does not need to wait for ambiguity to resolve. A qubit can natively represent a probability distribution rather than forcing a signal into a binary category. The raw, noisy probability field of the neural activity can be mapped directly onto the qubits, which process the entire distribution at once. The quantum system can decode the user's intention before the biological signal has even fully propagated through the neural pathway. This speed is the difference between a prosthetic that requires conscious effort to operate and one that responds as naturally as a biological limb. It is the difference between using a tool and having a body part. But the implications extend further than motor control. Motor signals are relatively simple because they encode specific muscle commands with a relatively limited vocabulary. Abstract thoughts are not. When you visualize a face, that visual pattern is distributed across dozens of cortical regions simultaneously. The information is encoded in the correlations between regions, not in any single stream of data. Classical algorithms struggle to read this because the number of variables is too high and the correlations are too subtle. A quantum system can analyze correlations across many brain regions in parallel, detecting the subtle synchronizations that represent specific memories, images, or concepts. This opens the possibility of decoding semantic thought directly, not just motor intention. If the latency is low enough and the decoding is accurate enough, the interface stops being an interface. The machine becomes a transparent extension of cognition. Communication does not require speech or gesture. The boundary between the biological mind and the digital processor becomes functionally invisible because information flows between them at biological speed. None of this is approaching its endpoint. It is approaching a beginning. Quantum computers today are still relatively small. The largest systems have hundreds of logical qubits, which is sufficient for demonstrating principles and solving narrow problems, but far short of what is needed to simulate even a simple neural circuit in full biological detail. The engineering challenges of scaling up these systems are formidable. Maintaining quantum coherence across thousands or millions of qubits while keeping error rates below the threshold required for accurate simulation is a problem that will require years of incremental progress. This is not a technology that will replace classical computing suddenly. The trajectory is toward a hybrid architecture. Future computational systems will almost certainly combine classical and quantum processors in a division of labor that exploits the strengths of each. The classical processor handles what it does best, the stable, structured, logical framework of the computation. It manages the input and output, maintains the static map of the connectome, and handles the bookkeeping. The quantum coprocessor handles what only it can do, the non-linear, probabilistic, entangled simulation of the dynamic neural activity. One system holds the skeleton, the other breathes life into it. This hybrid approach is likely how the first real-time simulation of a cortical column will be achieved. A cortical column is the basic repeating unit of the cerebral cortex. a cylindrical bundle of neurons about 2 millimeters tall and roughly half a millimeter in diameter, containing tens of thousands of cells organized into 6 distinct layers. It is the fundamental building block of higher cognition. Simulating one column in real time with full biological fidelity would be a transformative milestone. It would give researchers a living model of the core computational unit of the human brain. From there, scaling to a hemisphere becomes a matter of engineering rather than fundamental discovery. There is a deeper question lurking underneath all of this, one that cannot be deferred indefinitely as the technology matures. It is the question of consciousness itself. If we build a quantum simulation of a human brain that accurately replicates the energy states, the protein dynamics, the firing patterns, and the quantum fluctuations of biological neural activity, what exactly have we built? Have we built a model that calculates data, or have we built something that experiences the calculation? This is what philosopher David Chalmers calls the hard problem of consciousness. The easy problems of consciousness, in his terminology, are the ones that can be solved by good enough neuroscience. We can, in principle, explain how the eye encodes visual information, how the hippocampus consolidates memory, how the prefrontal cortex evaluates decisions. These are difficult engineering problems, but they are, in kind, the same as any other scientific problem. You build better tools, you measure more precisely, and eventually you have an explanation. The hard problem is different. It is the question of why any of that processing feels like something. Why does the specific pattern of activity associated with seeing red produce the subjective experience of redness? Why is there something it is like to be a brain? No equation in current physics answers this. There is no term in any Hamiltonian that corresponds to the feeling of sadness or the taste of sugar. The subjective dimension of experience exists outside the current scope of physical theory. Quantum mechanics offers an intriguing new angle on this problem. Integrated information theory, proposed by neuroscientist Giulio Tononi, argues that consciousness arises from the degree to which a system is irreducible. A conscious system is one where the whole is more than the sum of its parts, where the interactions between components generate information that cannot be decomposed into the sum of each component's individual contribution. The measure of this irreducibility is called phi. In a classical computer, components are separable. You can isolate one processor from another, information flows between them, but each component is, in principle, describable independently. In a quantum computer, entangled qubits are not separable. They form a unified wave function. You cannot describe the state of one qubit without describing the state of the whole entangled system. This physical unity corresponds to a high degree of irreducibility. If integrated information theory is correct, an entangled quantum system would naturally tend to exhibit a non-zero value of phi. Whether this is sufficient for consciousness remains unknown, but it is a more credible substrate for integrated information than anything classical computing provides. If this line of reasoning holds, then a sufficiently detailed quantum simulation of a brain might not merely model consciousness, it might instantiate it. And that possibility draws a boundary we have never had to draw before. If we create a quantum simulation of a human mind for the purpose of testing a drug, and that simulation generates signals consistent with pain, are we ethically obligated to treat those signals as meaningful? In a classical simulation, dismissing them as mere code is defensible. The classical computer is printing the words. The word pain and the state of pain are clearly different things. In a quantum simulation that is physically isomorphic to a brain in distress, the distinction becomes less clear. The physical state of the machine may be, in some morally relevant sense, the same as the physical state of a person suffering. This is not a distant philosophical puzzle. It is an engineering deadline. As quantum simulations become more detailed and more biologically accurate, the scientific community will need a framework for evaluating the moral status of simulated systems before the technology makes the question urgent. We do not currently have such a framework. We do not even have consensus on what features of a physical system give rise to experience in the first place. What researchers do have is a clearer understanding of the road ahead than at any previous point. The barrier between quantum computing and biological reality is narrowing from both directions. Biologists are finding more evidence of quantum processes inside the cell. Engineers are building quantum systems that are more stable, more scalable, and more precisely controllable. The convergence is no longer theoretical. It is a sequence of problems being solved one by one. Error correction was one of the central problems. The Willow chip addressed it in a decisive and unexpected way, demonstrating that the relationship between scale and stability in a quantum system can be engineered to be positive rather than destructive. That proof of concept removes one of the most fundamental arguments against scalable quantum computation. It does not mean the problem is solved at scale. It means we now know the problem is solvable. Qubit coherence time is another central problem. The longer a qubit can maintain its quantum state, the more complex the computation it can participate in. Coherence times have been increasing across different qubit architectures, including superconducting circuits, trapped ions, and photonic systems. Each architecture has different strengths and weaknesses. Superconducting qubits are fast, but require cooling to near absolute zero. Trapped ion qubits have longer coherence times, but operate more slowly. Photonic qubits are naturally suited for communication, but harder to control precisely. The diversity of approaches is itself a sign of a field in rapid development, exploring the space of solutions rather than converging prematurely on a single path. The question of how many qubits a useful brain simulation requires is still open. Estimates depend heavily on how much the biological model is simplified and what aspects of neural function the simulation prioritizes. A simulation focused only on the firing patterns of neurons without modeling the quantum behavior of individual proteins requires far fewer qubits than a full molecular scale simulation. The useful simulations will likely start at the more abstracted level and gain resolution as hardware improves. What will be learned from those simulations, even at reduced resolution, has the potential to be scientifically transformative. Computational neuroscience has always been limited by the fact that we cannot observe a living brain at full resolution and full speed simultaneously. When we image a brain with functional magnetic resonance imaging, we are averaging over millions of neurons and measuring activity on a timescale of seconds. When we record from individual neurons with electrodes, we see high resolution, but only in a tiny window of the brain. A real-time simulation provides a platform where you can observe every component at full resolution and full speed, run controlled experiments that would be ethically impossible in a living subject, and test theoretical models of cognition against a system that obeys the same physical laws as biology. This is the transformation that quantum brain simulation represents. Not just a faster computer, not just a more efficient drug discovery pipeline, not just a better prosthetic interface. It is a new kind of scientific instrument, one that allows us to study the brain from the inside, at the scale of physics, with the control of engineering. The progress is real, and it is accelerating. Google's Willow result was not an endpoint. It was a demonstration of principle that will be followed by successive generations of hardware. The collaboration between physics, engineering, neuroscience, and computer science working on this problem represents one of the most concentrated scientific efforts of the early 21st century. The people working in these fields are not working on incremental improvements. They are working toward a qualitative shift in what computation can do. What is still genuinely unknown is where the quantum signature in the brain actually lives. The evidence for quantum processes in microtubules is suggestive, but not yet conclusive. Replicating the results in controlled experiments with greater resolution is an ongoing challenge. Demonstrating unambiguously that quantum coherence persists long enough in a warm biological environment to influence neural computation requires measurements at the boundary of what current instrumentation can achieve. This is not a reason for skepticism. It is a reason for more careful science. What is also still unknown is how consciousness relates to the physical substrate. Integrated information theory is one framework. Global workspace theory is another. Predictive processing models offer yet another angle. None of them is definitively proven. None of them is definitively wrong. The hard problem remains hard. But the tools we are building to simulate the brain will generate data that bears directly on these questions in ways that pure philosophical analysis cannot. And that is what makes this moment unusual in the history of science. We are not just building a better tool, we are building a tool that will force us to confront questions we have previously been able to defer. Questions about what computation is, questions about what experience is, questions about where the boundary between model and reality lies. A quantum simulation of a brain, sufficiently detailed and sufficiently stable, will be a mirror that reflects not just the mechanics of cognition, but the question of what cognition actually is. We began by noticing an energy gap that the standard model of computation cannot explain. A 20-watt brain outperforming a megawatt supercomputer on the task of being itself. That gap was the first signal that the classical framework was missing something. The quantum framework does not erase the mystery, but it gives us a language capable of engaging with it. The brain speaks in probability, superposition, and entanglement. For the first time, we are building machines that speak the same language. Whether that shared language will eventually allow us to hear what the brain is actually saying about the nature of mind, that question remains open. And the fact that it remains open, that the science is still alive with uncertainty and possibility, is precisely what makes the next decade of this research worth watching. If these ideas captured your attention, consider subscribing, because the territory ahead is even more interesting than what we have covered here. To appreciate why quantum mechanics is the right language for the brain, it helps to understand the scale at which biology actually operates. We tend to think of biology as chemistry, and chemistry is something that happens at a level comfortably above quantum physics. That picture is wrong. The molecular machinery inside every cell operates at length scales where quantum effects are not peripheral, they are central. A water molecule is about 3 angstroms across. An angstrom is 1/10 billionth of a meter. The synaptic cleft, the gap across which neurotransmitters travel to transmit signals between neurons, is about 20 nanometers wide. A nanometer is 1 billionth of a meter. At these dimensions, the behavior of electrons is governed by quantum mechanical wave equations, not by the classical laws that describe billiard balls or planetary motion. The proteins that open and close ion channels in a neuron's membrane are molecular machines operating in this quantum regime. When a voltage-gated sodium channel opens to allow an action potential to propagate, the conformational change in the protein that opens the channel is driven by the quantum mechanical behavior of electrons and atomic nuclei. Classical mechanics cannot accurately describe it. It was never designed to. This is important because it means the brain is not a system that happens to be implemented in biology. It is a system whose fundamental operations are quantum mechanical. The neurons and synapses we see at the scale of cellular biology are the emergent, high-level output of processes that, at their foundation, are as quantum as any phenomenon studied in a physics laboratory. Simulating this system classically is not just slow, it is wrong in principle, in the same way that a classical model of hydrogen is wrong. It produces approximately correct answers in some regimes and completely breaks down in others. The distinction matters because it defines what we lose when we approximate. A classical simulation of the brain can capture the statistical behavior of neural firing rates and average connectivity patterns. It can reproduce the gross structure of neural dynamics and generate outputs that match experimental recordings at low resolution. What it cannot capture is the quantum correlations, the interference patterns, and the coherent energy transfer that may underlie the brain's most distinctive capabilities, including its efficiency, its flexibility, and possibly its capacity for subjective experience. A classical model of the brain is like a classical model of superconductivity. It works until it fails completely, and when it fails, no refinement within the classical framework can fix it. Richard Feynman, who thought more carefully than almost anyone about the relationship between physics and computation, came to this conclusion through reasoning about simulation rather than biology. His argument was simple and powerful. To simulate a quantum system on a classical computer, you need to track the amplitude of every possible quantum state of the system. For a system of n qubits or n quantum particles with 2 possible states each, the number of amplitudes you need to track grows as 2 raised to the power of n. For even a modest quantum system, this number rapidly exceeds any conceivable classical memory. A system of 300 entangled qubits would require more amplitudes to describe classically than there are atoms in the observable universe. You cannot fit the description of a 300 qubit quantum system into any storage medium made of matter. The brain contains vastly more than 300 quantum-relevant degrees of freedom. If even a small fraction of the neural processing involves quantum entanglement and coherence, the classical simulation is not just difficult. It is formally impossible at any scale of hardware that could ever be built. The only machine that can simulate a quantum system of that complexity is another quantum system of comparable complexity. This is Feynman's prescription made concrete. What makes the current moment significant is that we are finally building machines that approach this requirement. Not fully, not yet, but the trajectory is clear. The qubits of today's quantum processors are noisy and limited in number, but the error correction results of 2024 changed the outlook from theoretical possibility to engineering roadmap. There is now a defined path from where we are to where we need to be. The path is long, but it is no longer speculative. let us spend some time on what quantum mechanics actually does that classical mechanics cannot, because this is the foundation of everything else. In classical mechanics, a system has a definite state at every moment. A billiard ball is at a specific position moving in a specific direction with a specific energy. If you know the initial conditions precisely, you can predict the entire future trajectory of the system in principle. Reality, in the classical picture, is deterministic and definite. Quantum mechanics replaces this with a different picture. A quantum system is described not by a definite state, but by a wave function. The wave function encodes the probability amplitudes for every possible measurement outcome. When you ask where a particle is, the wave function gives you not an answer, but a probability distribution of possible answers. The particle does not have a definite position before you measure it. It has a superposition of positions. Measurement collapses the superposition to a single outcome, but before measurement, all outcomes coexist. This is not a statement about our ignorance. It is a statement about reality. The particle genuinely does not have a definite position before measurement. This was confirmed by a series of experiments testing what are called Bell inequalities, following theoretical work by physicist John Bell in 1964. Bell showed that if quantum particles had definite values of their properties before measurement, hidden from us but objectively real, then certain correlations between measurements on separated particles would have to obey specific mathematical bounds. Experiments, beginning with those of Alain Aspect in the 1980s and continuing with increasing precision to the present day, have consistently violated these bounds. The violations mean the particles genuinely do not have pre-existing definite values. The quantum description is not a shorthand for classical ignorance. It is a description of how nature actually is. For computation, this means something specific. When qubits are placed in superposition, the computation genuinely explores multiple branches simultaneously. This is not parallelism in the sense of having multiple processors each working on one branch. It is the exploration of multiple branches within a single physical system, governed by the mathematics of quantum interference. The wrong answers interfere destructively and cancel out. The right answer interferes constructively and emerges. This is fundamentally different from anything a classical system can do, because a classical system can only follow one branch of possibility at a time, even if it has many processors working in parallel. For simulating physical systems, including the brain, this means a quantum computer can evolve the simulation through time using the same equations that govern the actual physics. The qubits enact the Hamiltonian rather than computing its consequences numerically. The simulation does not fall behind the reality it is modeling because it is running the same physical laws. This is the sense in which quantum simulation is qualitatively different from classical simulation. It is not faster, it is more accurate. It does not approximate the physics, it performs it. The coherence that makes this possible is also what makes it difficult to engineer. Quantum coherence, the property by which different possible states of a quantum system maintain fixed phase relationships and therefore interfere with each other, is destroyed by interaction with the environment. Any coupling between the quantum system and its surroundings causes the superposition to leak information into the environment, and the quantum state collapses toward a classical mixture of possibilities. This process is called decoherence, and it is the central engineering challenge of quantum computing. In the laboratory, decoherence is fought by isolating the quantum processor from its environment as thoroughly as possible. Superconducting qubit chips are cooled to temperatures around 15 millikelvin, colder than outer space, to suppress thermal vibrations. They are shielded from electromagnetic radiation. The control signals sent to the qubits are designed to minimize unintended coupling. Even with all these precautions, the coherence time of individual qubits is limited to microseconds or, in the best systems, milliseconds. In the brain, the environment is exactly the opposite of a carefully isolated quantum laboratory. The temperature is 310 degrees Kelvin, close to thermal equilibrium. The cell is filled with water, which is an aggressive source of decoherence because water molecules are polar and constantly interact with charged molecules. The cell membrane is subject to constant mechanical vibration, and yet, as we have seen, quantum effects in biological systems have been observed. This apparent contradiction, quantum coherence surviving in a warm, wet environment, has become one of the most interesting open questions in biophysics. The resolution may lie in the timescales involved. Decoherence in biological molecules occurs extremely quickly, often in femtoseconds. But the relevant biological processes, such as energy transfer in photosynthesis or conformational changes in ion channels also occur on femtosecond timescales. The quantum coherence does not need to survive for a long time. It needs to survive long enough to influence the next step in the biological process. If the chemical reaction completes faster than the coherence decays, the quantum effect has done its work. The warm, wet environment that seems hostile to quantum mechanics may be irrelevant if the quantum events are over before the environment can destroy them. This is why the analogy between quantum computers and quantum biology is imperfect but illuminating. A quantum computer is engineered to maintain coherence over millions or billions of gate operations. A biological system uses quantum effects for a single fast step and then allows decoherence. The strategies are different, but the underlying physics is the same. Both are exploiting the wave nature of matter to accomplish something that would be impossible if reality were purely classical. Understanding this distinction also clarifies what a quantum simulation of the brain is actually trying to achieve. The goal is not to build a machine that maintains quantum coherence in exactly the same way the brain does, at exactly the same temperature, with exactly the same noise profile. The goal is to build a machine whose quantum dynamics are governed by the same Hamiltonian as the brain's dynamics. The hardware can be very different from the biology as long as the underlying mathematics is the same. This is why superconducting circuits cooled to 15 millikelvin can, in principle, simulate a warm biological system. The physics of the simulation is what matters, not the physical substrate. This principle of substrate independence is one of the most profound ideas in the theory of computation. A computation is defined by its logical structure, not by the physical system carrying it out. The same computation can run on silicon transistors, on vacuum tubes, on mechanical gears, or on quantum circuits. What distinguishes quantum computation from classical computation is not the hardware. It is the class of logical operations that the hardware can natively perform. A quantum processor can natively perform operations that are impossible on any classical machine, regardless of how fast the classical machine runs. This is the boundary that matters. For brain simulation, the relevant native operations are quantum simulations of physical Hamiltonians. A classical processor cannot perform these operations natively. It can only approximate them through numerical methods that become exponentially expensive as the system size grows. A quantum processor performs them directly. This is not a matter of degree, it is a matter of category. The implication is that a quantum simulation of the brain is not just a better version of what classical simulators have attempted, it is a different kind of thing entirely. Classical brain simulations are models in the conventional scientific sense. They are mathematical descriptions of how we believe the system behaves, encoded in computational form. A quantum simulation of the brain aspires to be a physical instantiation of the brain's dynamics, not a description of what the brain does, but an enactment of it. The language of the simulation and the language of the biology are the same language. Let us now return to the connectome and think about what it means to simulate it properly. The connectome is the complete map of neural connections in a brain. For a human brain, this map is enormously complex, but mapping the connections, knowing which neuron is connected to which other neuron and with what synaptic strength, is only the beginning. The map is static. The brain is dynamic. To simulate the brain, you need to not only know the architecture, but to model how activity propagates through that architecture in real time, how synaptic strengths change in response to activity, how neuromodulatory signals globally alter the processing of local circuits, and how all of these processes interact simultaneously across the whole network. The first complete connectome ever mapped, at the level of individual neurons and synapses, was the connectome of Caenorhabditis elegans, a tiny roundworm with 302 neurons and approximately 7,000 synapses. This project was completed in the 1980s and took over a decade of manual reconstruction from electron microscopy images. With that complete map, researchers could simulate the worm's nervous system classically, and the simulations were informative. But they also revealed something important. Even with the complete connectivity map, the classical simulation could not fully reproduce the worm's behavior. Something was missing. The map was necessary but not sufficient. The missing elements are the dynamic properties of the neurons themselves, including their intrinsic excitability, the kinetics of their ion channels, the spatial distribution of inputs across the dendritic tree, and the probabilistic nature of synaptic transmission. All of these properties are quantum mechanical at their foundation. A classical simulation can parameterize them, meaning it can represent them with equations fitted to experimental data. But parameterization is not simulation. It replaces the physics with a model of the physics, and the model is always an approximation. The approximation is acceptable for some purposes. For others, particularly those involving the subtle quantum effects that may underlie phenomena like memory consolidation and consciousness, the approximation may discard exactly the information that matters. The Human Connectome project, launched in 2009 with funding from the United States National Institutes of Health, set out to map the large-scale connectivity structure of the human brain using diffusion MRI tractography. This technique traces the pathways of white matter fiber bundles connecting different brain regions. It does not resolve individual neurons and synapses, but it provides a macro-scale map of interregional connectivity. This macro-scale connectome has been used to build computational models that capture some aspects of large-scale brain dynamics, including the resting state patterns of correlated activity seen in functional MRI. These models have generated useful insights. They have helped identify which patterns of connectivity are associated with different cognitive states. They have provided frameworks for understanding how brain lesions disrupt cognition based on the structural role of the damaged region in the connectivity network. But they cannot simulate the neural activity itself. They model statistical patterns at a spatial and temporal resolution far coarser than the actual neural dynamics. They are maps, not territories. The territory requires knowing what is happening at the synapse, at the ion channel, at the protein level, and at each of those levels, the relevant physics is quantum mechanical. This is why the two research programs, classical large-scale connectome modeling and quantum simulation of neural dynamics, are not competing with each other. They are addressing different levels of description that will ultimately need to be integrated. The macro-scale connectome provides the architectural blueprint. The quantum simulation provides the means to execute the blueprint faithfully. There is also a dimension of this problem that is rarely discussed: the role of glial cells. For most of the history of neuroscience, glial cells were considered to be the support staff of the brain, providing structural scaffolding, supplying nutrients to neurons, and maintaining the ionic environment that allows neurons to fire. They were thought of as passive. Research over the past 2 decades has overturned this picture substantially. Glial cells, particularly the astrocytes, are now understood to actively participate in neural signaling. Astrocytes form intimate contacts with synapses. A single human astrocyte can enwrap as many as 2 million synapses. At each synapse, the astrocyte monitors the chemical environment and releases its own signaling molecules, called gliotransmitters, which modulate synaptic strength. Astrocytes also propagate calcium waves that travel through networks of connected astrocytes at speeds and over distances that are relevant to neural computation. The brain has as many astrocytes as it has neurons. A simulation that ignores astrocytes is ignoring half the computational substrate. Including astrocytes in a brain simulation adds a layer of complexity that further highlights the inadequacy of classical approaches. The calcium dynamics inside an astrocyte involve the same quantum mechanical protein behaviors that govern ion channel opening in neurons. The release of gliotransmitters involves the same quantum-level conformational changes in molecular machines. A complete simulation must simulate not just the neurons, but the entire cellular ecosystem of the brain. Quantum hardware capable of simulating the full molecular dynamics of a single synapse, including the presynaptic terminal, the synaptic cleft, the postsynaptic density, and the surrounding astrocytic processes, would already be a scientific instrument of extraordinary power. A simulation covering the full brain remains a longer-term goal. One area where the near-term payoff is most concrete is in the simulation of anesthetic mechanisms. Anesthetics are among the most widely used drugs in medicine, yet the mechanism by which they render a patient unconscious is still not fully understood at the molecular level. This is a remarkable admission. We have been routinely inducing unconsciousness in surgical patients since the 1840s, and we do not know exactly how it works. What we do know is that anesthetics interact with proteins in neural membranes, and that Roger Penrose and Stuart Hameroff have argued specifically that anesthetics act on microtubules, supporting their theory that microtubules are involved in consciousness. The idea is that if anesthetics disrupt quantum processing in microtubules, this would explain why they eliminate consciousness without simply killing the neurons. The neurons survive anesthesia. Their electrical activity continues to some extent. What disappears is the integrative experience that we call being awake. If this is correct, A quantum simulation of microtubule dynamics under anesthetic exposure would directly illuminate the physical mechanism of consciousness. It would also explain why patients wake up when the anesthetic clears. The quantum processing in the microtubules resumes. This hypothesis is testable, and the fact that it is testable is what makes quantum simulation of biological systems scientifically valuable. Competing theories of consciousness make different predictions about what a sufficiently detailed simulation would show. A simulation capable of faithfully reproducing the molecular dynamics of neural tissue would provide a platform for discriminating between these theories in a way that purely conceptual analysis cannot. We would be running experiments on the physical substrate of mind. To simulate these dynamics requires not just quantum hardware, but also advances in how quantum computers are programmed and controlled. Quantum algorithms for simulating molecular dynamics, called variational quantum eigensolvers, and quantum phase estimation algorithms have been developed and tested on small systems. They work. The results match what we expect from classical quantum chemistry calculations. The limitation is that the systems they can handle are still small, on the order of dozens of electrons in a molecular orbital structure. Scaling these algorithms to handle proteins with thousands of atoms requires hardware that does not yet exist at the required scale, but the algorithms themselves are ready. There is also a growing body of work on quantum machine learning algorithms that are specifically relevant to the problem of decoding neural activity. Classical machine learning has been successfully applied to decode motor intentions from neural recordings, enabling basic brain-computer interfaces. But classical decoders face fundamental limitations in the quality and speed of decoding complex cognitive states. Quantum machine learning algorithms, which run on quantum hardware, can in principle find patterns in high-dimensional data that classical algorithms cannot detect efficiently. Applying these to the high-dimensional probability distributions of neural activity could dramatically improve the quality and latency of brain-computer interface decoding, even before a full brain simulation is achieved. The interaction between quantum computing and neuroscience is therefore not a single monolithic project. It is a collection of converging research programs, each addressing a specific aspect of the grand challenge, and each capable of delivering scientifically and medically meaningful results at different points along the development timeline. Error correction research advances the stability of quantum hardware. Quantum chemistry algorithms advance our ability to simulate molecular-level neural processes. Quantum machine learning algorithms advance the quality of brain-computer interfaces. And foundational research into quantum effects in biological systems advances our understanding of whether and how the brain itself uses quantum mechanics. All of these programs are active today. They are being pursued in academic laboratories, government research agencies, and private companies simultaneously. The fact that multiple independent lines of research are converging on the same set of questions is itself evidence that the questions are real and tractable, not speculative. There is one more dimension of this topic that deserves careful attention, and it concerns the distinction between artificial intelligence and what might be called neuromorphic quantum intelligence. Modern artificial intelligence systems, particularly the large language models that have become prominent in public discourse, are trained by exposure to data. They learn statistical patterns in text, images, or other data types and generate outputs that reflect those patterns. They are extraordinarily sophisticated pattern matchers. They can produce fluent text, recognize images, write code, and generate plans. They are also brittle in ways that biological intelligence is not. They fail at problems that require genuine reasoning outside their training distribution. They lack the flexible generalization that characterizes human cognition. The reason for this brittleness is architectural. These systems are trained to minimize a loss function over a training dataset. Everything they know is derived from what they have seen. They have no way to engage with novel problems by reasoning from first principles, because first principles require access to the underlying physics of the world, which is quantum mechanical and which cannot be captured in a dataset of text and images. A quantum simulation of neural dynamics is a different kind of thing. It is not trained on data, it is built from physics. Its behavior emerges from the same equations that govern the behavior of the actual biological system it is modeled on. If the model is sufficiently accurate, it does not just replicate what we know. It can explore what we do not know, because it is running the same physics that the brain runs. It can discover things that are not in any dataset because it is operating from the same first principles as nature. This distinction between statistical pattern matching and physical enactment is fundamental. An artificial intelligence system can tell you things that are consistent with the patterns in its training data. A quantum neural simulation can do experiments. It can be given novel conditions that were never part of any training dataset and generate responses by following the physics, not by extrapolating from examples. This is the difference between an encyclopedia and a laboratory. The implications for our understanding of cognition itself are profound. The history of science is full of examples where a powerful new instrument opened a window onto phenomena that were previously invisible. The telescope revealed the moons of Jupiter and the craters of the Moon, overturning the Aristotelian picture of perfect celestial spheres. The microscope revealed the cellular structure of living tissue, overturning the humoral theory of disease. The functional MRI scanner revealed the large-scale patterns of neural activity during cognition, overturning the localizationist view that individual cognitive functions were confined to small, fixed brain regions. A quantum brain simulator would be an instrument of this same category. It would reveal aspects of neural dynamics that are currently invisible to all existing tools. What we do not know is exactly what it will reveal. This is the nature of instrument-driven discovery. The most important findings are the ones we could not have predicted in advance, because if we could have predicted them, we would not have needed the instrument. The history of the telescope and the microscope should make us appropriately humble about our ability to anticipate what quantum simulation of the brain will teach us. We can identify the questions it will help answer. We cannot know what new questions it will open. The people working in this field are motivated by exactly this kind of scientific excitement. The theoretical frameworks we have for understanding consciousness, cognition, and neural computation are, in important ways, incomplete. We know they are incomplete because the experimental evidence from neuroscience repeatedly produces results that do not fit neatly into existing frameworks. Animals display behavioral flexibility that does not fit simple stimulus-response models. Human cognition displays contextual sensitivity that does not fit rule-based models. Consciousness displays properties of unity and continuity that do not fit connectionist models of separate, interacting modules. Something is missing from our understanding. The tools we have built so far are not precise enough to find it. The quantum brain simulation program is, at its deepest level, a search for that missing piece. It is not guaranteed to find it. Science never is. But it is the most physically honest approach we have developed. It takes seriously the fact that the brain is a quantum mechanical system and builds instruments accordingly. The alternative, continuing to simulate the brain with tools that are structurally incapable of capturing its physical reality, is not a path to understanding. It is a path to increasingly sophisticated approximations that will always leave the hardest questions unanswered. We are at a point in history where the tools are catching up to the questions. The quantum hardware is advancing faster than many experts predicted a decade ago. The theoretical frameworks connecting quantum mechanics to neuroscience are becoming more precise and more testable. The experimental techniques for probing quantum effects in biological systems are becoming more sensitive. The convergence is real and it is accelerating. The gap between where we are and where we need to be is still large. The engineering challenges of building a quantum simulator capable of modeling a full human brain in real time are formidable. The scientific challenges of understanding how to parameterize such a simulation, how to validate its outputs, and how to extract meaningful scientific conclusions from it are equally formidable. No one working in this field believes the problem will be solved in the next few years, but no one working seriously in this field believes it will remain unsolvable. What the field believes, with increasing confidence, is that the approach is correct, that quantum simulation is the right framework for understanding the brain, that the discrepancy between classical computational approaches and biological reality is not a gap to be closed by more engineering, but a fundamental signal that the physical foundation must be rethought, and that rethinking that foundation, building computers that speak the language of physics rather than the language of binary logic, is the most important engineering project of the coming decades. We began with the observation that the brain and the classical computer are running on different physics. We have traced that observation through the biology of the neuron, the thermodynamics of computation, the quantum behavior of biological molecules, the architecture of quantum processors, the breakthrough in error correction, and the applications ranging from drug discovery to brain-computer interfaces to the fundamental question of consciousness. Each step in that journey has reinforced the same conclusion. The brain is a quantum system. To understand it, We need quantum tools, and for the first time in the history of science, those tools are within reach. What happens when we build them will reshape not just neuroscience and medicine, but our deepest understanding of what minds are, what matter can do, and what it means to think. These are not small questions. They are the questions that have animated philosophy and science for centuries. The fact that they are now approaching the domain of experiment, that we may in our lifetimes build machines capable of generating data that bears directly on these questions, is extraordinary. The universe is made of quantum mechanics. The brain is made of the universe, and we are finally building computers made of the same physics as both. To understand where the technology goes from here, it helps to look at the specific milestones that researchers in this area are working toward and the order in which they are likely to be achieved. The progression is not random. It follows the logic of the underlying physics and the constraints of what hardware can currently do. The first milestone, which is already being achieved in laboratory settings, is demonstrating quantum advantage for specific quantum chemistry problems relevant to biology. Quantum advantage means showing that a quantum computer can solve a problem that is beyond the practical reach of any classical computer, regardless of how long you let the classical machine run. For quantum chemistry, the target problems involve calculating the ground state energy of molecular systems, the same calculation that underlies protein folding and drug receptor binding. The variational quantum eigensolver algorithm has been used to calculate the ground state energies of small molecules like hydrogen and lithium hydride on existing quantum hardware. These are systems with a handful of electrons. The goal in the near term is to scale these calculations to molecules with dozens or hundreds of electrons, which is the regime relevant to the active sites of biological proteins. The second milestone is demonstrating quantum simulation of a biologically realistic ion channel. Ion channels are the molecular switches of the nervous system. They are transmembrane proteins that open and close in response to voltage or chemical signals, allowing specific ions to flow across the cell membrane. This flow of ions is what generates the electrical signals that neurons use to communicate. An ion channel is small enough, on the order of a few hundred amino acids, to be within reach of near-term quantum simulation. And accurate simulation of an ion channel would be directly scientifically valuable because many neurological diseases are caused by mutations in ion channel genes, and many drugs work by blocking or modulating ion channel activity. The third milestone is the quantum simulation of a synaptic release event. When a nerve impulse reaches the end of an axon, it triggers the release of neurotransmitter molecules from small vesicles into the synaptic cleft. This process involves a cascade of molecular events, including the activation of voltage-gated calcium channels, the binding of calcium ions to proteins called snares, the conformational change of the snare complex that pulls the vesicle membrane into contact with the cell membrane, and the fusion of the two membranes that releases the neurotransmitters. Each step involves quantum mechanical processes in proteins. A quantum simulation of a single synaptic release event would be a landmark achievement because it would, for the first time, give us a physically accurate picture of how the most fundamental unit of neural communication actually works. Beyond these specific milestones, there are broader architectural developments in quantum computing that will enable larger-scale neural simulations. One of the most important is the development of quantum networks, systems in which multiple quantum processors are connected to each other through quantum communication channels. The brain's computational power comes not from any single neuron, but from the network. A quantum simulation of the brain will similarly need to be distributed across a network of quantum processors, each simulating a local region of the brain connected by quantum channels that allow entanglement to be maintained across the whole system. Quantum networking is itself an active area of research, driven in part by applications in quantum cryptography and distributed quantum computing. The basic building blocks of quantum networks, quantum repeaters, entanglement distribution systems, and quantum memory nodes are being developed and tested. A functional, large-scale quantum network would be transformative, both for communication security and for distributed quantum simulation. Another important development is the maturing of quantum programming languages and compilers. Programming a quantum computer is qualitatively different from programming a classical one. On a classical computer, you write instructions that the processor executes sequentially or in parallel. On a quantum computer, you design circuits of quantum gates that transform the state of the qubits in specific ways. The mapping from high-level scientific intent to low-level qubit operations is non-trivial. and errors in this mapping can cause the simulation to produce results that are physically meaningless. Quantum programming languages like Qiskit, Cirq, and PennyLane are being developed to make this process more tractable, and quantum compilers that optimize circuits for specific hardware architectures are becoming increasingly sophisticated. These software tools are as important as the hardware, because without them, the hardware cannot be effectively used. The question of validation is also central. When we build a quantum simulation of a neural system, how do we know it is correct? For small systems where classical computation is still possible, we can compare the quantum simulation result to the classical result. But for the large systems where quantum simulation is the only option, there is no classical benchmark. Validating a quantum simulation of a neural circuit that is beyond classical computation requires new experimental strategies. One approach is to make predictions from the simulation and test them against experiment, comparing the simulation's output to recordings from real neural tissue. Another approach is to use mathematical properties of quantum systems, like conserved quantities, to verify that the simulation is behaving correctly internally. Developing these validation methodologies is an active area of research that runs parallel to the hardware and algorithm development. There is also an emerging field that connects quantum biology directly to quantum computing in a feedback loop. As researchers discover more about the specific quantum processes that operate inside neurons and other biological cells, the knowledge can be used to better design quantum simulations. And as quantum simulations generate predictions about biological quantum dynamics, those predictions can be tested in experiments on living cells. This iterative loop between theory, simulation, and experiment is the same process that has driven progress in all areas of physics. It is beginning to take shape in the emerging field of quantum neuroscience. The researchers at the forefront of this field come from extraordinarily different backgrounds. Quantum physicists who have spent careers understanding the behavior of superconducting circuits or trapped ions are collaborating with neuroscientists who have spent careers recording neural activity in living animals. Chemists who understand protein folding are working with computer scientists who design quantum algorithms. The collaboration across these disciplines is not always easy. The languages are different, the timescales are different, the culture of progress is different, but the convergence is real and productive. One of the clearest signs of the seriousness with which the scientific community is taking this convergence is the level of investment from both public funding agencies and private enterprise. The United States Department of Energy has funded quantum simulation programs specifically aimed at biological applications. The European Union's Quantum Flagship program has included quantum simulation of complex systems as a priority area. Private companies including Google, IBM, Microsoft, and a growing ecosystem of quantum startups have all made quantum simulation a central part of their roadmaps. The involvement of commercial entities reflects a recognition that the applications of quantum simulation are not limited to pure scientific understanding. Drug discovery is a trillion-dollar industry that is genuinely limited by the accuracy and speed of molecular simulation. Brain-computer interfaces are a rapidly growing field that is genuinely limited by decoding latency. Neurological diseases affect hundreds of millions of people worldwide and represent an enormous unmet medical need. The commercial incentives are aligned with the scientific goals in a way that is relatively rare in science and technology. This alignment accelerates progress. It also creates challenges. Commercial timelines favor results that can be demonstrated quickly and monetized near term. Scientific understanding of consciousness and fundamental quantum biology operates on timescales that are incompatible with quarterly earnings cycles. Maintaining the foundational research programs while also pursuing near-term applications requires careful management of resources and priorities. The scientific community is well aware of this tension and is actively working to preserve space for long-horizon fundamental research within an environment increasingly shaped by commercial considerations. What is not in doubt is that the direction of travel is correct. Every piece of evidence that has emerged over the past decade, from the error correction results of Google's Willow chip, to the quantum coherence measurements in biological molecules, to the protein folding breakthroughs that have revealed the molecular machinery of neurodegeneration in unprecedented detail, all of it points in the same direction. The brain is a quantum system. Understanding it requires quantum tools, and the quantum tools are becoming real. When we zoom out and consider the full arc of this story, from the observation that the brain is impossibly efficient by classical standards, through the discovery of quantum effects in biological molecules, through the development of quantum hardware capable of maintaining coherent states long enough to run meaningful simulations, to the prospect of a real-time quantum simulation of neural dynamics, we are looking at one of the most significant intellectual transitions in the history of science. We are watching the moment when the study of mind and the study of matter converge into the same inquiry. For most of history, mind and matter have been studied separately. Philosophy investigated the nature of mind through reason and introspection. Physics investigated the nature of matter through experiment and mathematics. The two inquiries occasionally touched, as they did when the founders of quantum mechanics grappled with the measurement problem and the role of the observer. But they remained largely separate. The tools of physics were not applicable to the brain, and the questions of philosophy were not answerable by physics. Quantum brain simulation changes this. It brings the brain fully within the domain of physics. It subjects the organ of mind to the same experimental and theoretical treatment that physics has applied to atoms and particles and fields. It makes the question of consciousness not a philosophical puzzle to be pondered, but a scientific question to be investigated by building precise instruments and making precise measurements. This is a profound shift. Its consequences will take decades to fully unfold. But the shift is underway. We do not know what we will find when we have instruments precise enough to look. The history of science teaches us that the findings of transformative new instruments are always surprising. The quantum simulation of the brain will almost certainly reveal phenomena that do not fit our current frameworks, forcing us to revise and extend those frameworks in ways we cannot fully anticipate. This is not cause for anxiety, it is cause for excitement. It means that the most interesting chapters of this story have not yet been written. What we can say with confidence is that the story is real, the physics is right, the biology is consistent with the physics. The engineering is advancing along a trajectory that makes the long-term goals achievable. The questions being asked are the deepest questions in science, and the answers, when they come, will matter. If you found this journey through quantum mechanics and neuroscience as fascinating as the people spending their careers on it clearly do, consider following along as the science develops. The next results from quantum hardware will be significant. The next discoveries about quantum effects in biological systems will be significant. The next milestones in brain-computer interfaces will be significant. This is an area where the news from the laboratory genuinely changes what is possible to think. That is a rare thing, and it is happening now. Let us go deeper into something that the mainstream discussion of quantum computing almost always skips over, and that is the question of what the brain is actually optimizing for. Classical computers are designed to optimize for a specific output, the correct answer to a well-defined problem. You give the machine a question, it computes the answer, and you evaluate whether the answer is right or wrong. This is an enormously useful thing to do, but it is not obviously what the brain is doing. The brain did not evolve to solve calculus problems, it evolved to keep an organism alive in a complex, uncertain, rapidly changing environment. That goal requires a completely different computational strategy. An organism facing a predator cannot afford to wait for a guaranteed optimal solution. It needs a fast, good enough decision, and it needs to make that decision under conditions of severe uncertainty with incomplete information, under time pressure, while simultaneously managing 100 other physiological processes. The brain's architecture reflects these constraints at every level. One of the most striking features of neural processing that reflects this imperative is predictive coding. The prevailing model of visual processing used to be feed-forward. Light hits the retina, signals propagate through a hierarchy of visual areas, and somewhere at the top of the hierarchy, an object is recognized. This model is wrong, or at least deeply incomplete. The brain's visual system is not primarily a bottom-up signal processor. It is a prediction machine. At every level of the visual hierarchy, higher brain areas are sending predictions downward, anticipating what the lower areas are about to signal based on prior experience and current context. The lower areas compare the incoming sensory signal with the prediction from above. If the signal matches the prediction, almost nothing happens. If the signal deviates from the prediction, a prediction error is sent upward. Only the unexpected, the things that violate the brain's model of the world, generate strong neural activity. The brain is running a constant simulation of its environment and updating that simulation based on deviations from prediction. This predictive coding framework means that the brain is not primarily processing reality. It is constructing a model of reality, verifying it against incoming data, and updating it when wrong. The subjective experience of perceiving the world is, in this framework, largely a simulation generated by the brain's internal model, with sensory data serving mainly as error signals that correct the simulation when it goes off course. This is a radical reconceptualization of perception, and it has profound implications for what a brain simulation must reproduce. A quantum simulation of the brain that accurately models neural dynamics must therefore model not just the passive processing of sensory signals, but the active generation of predictions. It must model how prior experience shapes the expectations that are projected downward from higher to lower brain areas. It must model how prediction errors propagate upward and how they update the internal model. This is a much richer computational picture than the simple feed-forward circuit diagrams that dominated neuroscience for decades. And it is a picture that maps naturally onto the quantum mechanical framework, because quantum mechanics is itself a theory about probabilities and their updates in response to measurement. The Bayesian brain hypothesis, which generalizes predictive coding to a full statistical framework, argues that the brain is essentially implementing Bayesian inference. Given a prior distribution over possible states of the world and incoming sensory data, the brain computes the posterior distribution, the updated probability distribution over world states given the data. This is optimal inference under uncertainty. It is also computationally expensive for a classical system because exact Bayesian inference in high-dimensional spaces is exponentially hard. The brain must be implementing some efficient approximation. Understanding what approximation the brain uses and whether it involves quantum mechanical sampling is an active area of research. One intriguing hypothesis is that the brain implements approximate Bayesian inference using quantum sampling. Quantum systems naturally sample from probability distributions that are defined by their wave functions. If the brain's quantum dynamics effectively implement a quantum sampling process over the space of possible world states, the result would be approximate Bayesian inference at biological speed and efficiency. This would explain both the brain's remarkable efficiency and its characteristic pattern of errors and biases in perception and decision-making. The brain would not be calculating the Bayesian posterior exactly. It would be sampling from a quantum approximation of it. The samples would be distributed according to the correct probabilities in the limit, but individual inferences would carry the noise of finite sampling. This hypothesis makes a specific prediction. The brain's perceptual and cognitive errors should follow the statistics of quantum sampling from a Bayesian posterior, rather than the statistics of deterministic classical approximation. Testing this prediction requires experiments that measure the statistics of perceptual decisions with enough precision to distinguish the two, and quantum simulations that can generate quantitative predictions about what those statistics should look like. This is at the frontier of current research. If the hypothesis is correct, it would mean that the brain's architecture is not just efficient in an engineering sense, it is optimal in a physical sense. It is the most efficient possible way to implement probabilistic inference given the physical resources available to it. Evolution, which is itself a process of optimizing fitness over millions of generations, may have discovered the quantum mechanical foundation of optimal inference and built it into every neuron. This is a remarkable idea, and it is testable. The idea also connects to a broader theme that has emerged from the study of quantum biology, that living systems are not just subject to the laws of physics, but have evolved to exploit them in sophisticated ways. Photosynthesis, as mentioned earlier, uses quantum coherence to route energy efficiently from light harvesting complexes to the reaction center. The navigation of migratory birds may exploit quantum entanglement in cryptochrome proteins to sense the direction of the Earth's magnetic field. The sense of smell may involve quantum tunneling of electrons in odorant molecules. In each of these cases, evolution has not been limited to the crude material of classical mechanics. It has dug down to the quantum level and found there mechanisms of efficiency and sensitivity that classical processes cannot match. The brain, as the most complex biological organ and the one subject to the most intense selection pressure, should be expected to have exploited quantum mechanics more extensively and more sophisticatedly than any other biological system. The evidence is accumulating that it has, and the quantum simulation program is designed to follow that evidence wherever it leads. There is a philosophical dimension to all of this that is worth spending a moment on, not because philosophy can resolve the scientific questions, but because it helps clarify what is genuinely at stake. The question of whether a quantum simulation of a brain would be conscious is not just a question about the simulation, it is a question about the nature of consciousness itself. And the answer, Whatever it turns out to be, will have implications that reach far beyond neuroscience or computer science. If consciousness is a purely physical phenomenon that arises from specific patterns of quantum information processing, then in principle, it could arise in any physical system that implements those patterns, biological or not. This is the position implied by both integrated information theory and the orchestrated objective reduction theory of Penrose and Hameroff. On this view, consciousness is substrate independent in the sense that it depends on the structure of the information processing, not on the specific material implementing it. A quantum simulation of a brain, if sufficiently accurate, would be as conscious as the brain it simulates. If, on the other hand, consciousness requires something beyond physical information processing, some additional ingredient that physics has not yet described, then no simulation, however accurate, would produce consciousness. This is a minority position in contemporary philosophy of mind, but it is not obviously wrong. The hard problem of consciousness is genuinely hard precisely because we do not have a framework for deriving subjective experience from physical processes, quantum or otherwise. The explanatory gap between third-person physical description and first-person subjective experience remains open. What the quantum simulation program will do, regardless of which philosophical position turns out to be correct, is generate vastly more precise empirical data about the relationship between physical processes and experience. It will allow us to ask questions like, what specific changes in quantum dynamics correspond to the transition from unconsciousness to consciousness induced by anesthesia? What quantum signatures distinguish the neural dynamics of attention from those of inattention? What physical processes correlate with the onset and resolution of pain? These are empirical questions. They can be investigated experimentally, and their answers will constrain the space of possible philosophical frameworks. Science does not typically resolve philosophical questions by force of argument. It resolves them by making some arguments consistent with evidence and others inconsistent with it. The measurement of the cosmic microwave background did not prove or disprove the philosophical question of whether the universe had a beginning. It made some theories of the universe's beginning consistent with observation and others inconsistent. In the same way, quantum simulation of the brain will not prove or disprove the hard problem of consciousness by philosophical argument, but it will generate data that some philosophical frameworks can accommodate and others cannot. This is the appropriate relationship between science and philosophy. Philosophy identifies the deep questions and clarifies what would count as evidence. Science generates the evidence. The two are not competing. They are partners in an inquiry that is larger than either can pursue alone. Looking at this from the furthest remove, the quantum brain simulation program represents a specific moment in the long history of science's attempt to understand nature from the inside out. Every major scientific revolution has involved discovering that the world is stranger and more interesting than our intuition suggested. Classical mechanics suggested a deterministic, clockwork universe. Quantum mechanics revealed a universe of probability and uncertainty. Special relativity revealed that space and time are not absolute but relative to the observer. General relativity revealed that gravity is not a force but the curvature of space-time. Each of these revelations required abandoning intuitions that felt certain and replacing them with frameworks that were initially counterintuitive but turned out to be physically accurate. The quantum brain simulation program is following the same logic. Our intuition tells us that the brain is a classical machine because the brain is large, warm, and operates on timescales we can perceive, but the physics says otherwise. The physics says that the processes underlying cognition are quantum mechanical at their foundation. And if history is any guide, the physics is right and the intuition will need to be revised. What comes after the revision is hard to predict in detail, but the general direction is clear. We will have a more accurate physical picture of what the brain is. We will have tools capable of simulating that physics with unprecedented accuracy. We will be able to ask questions about cognition, consciousness, and mental health that are currently unaskable. And we will have to grapple with new ethical questions about the moral status of systems that implement the physics of thought. These are the challenges and the opportunities that lie ahead. They are not small, they are not simple. They are exactly the kind of challenges that science at its best is equipped to face: empirical, rigorous, humble in the face of uncertainty, and animated by genuine curiosity about the nature of things. The gap between classical computing and the brain has been visible for decades. We measured it in watts, in synapses, in seconds of simulation time. We diagnosed it as a fundamental incompatibility between the physics of silicon and the physics of biology. Now we are building, step by step, the tools to bridge it. The qubits are getting cleaner, the error rates are falling, the algorithms are becoming more sophisticated, the biology is revealing its quantum architecture more clearly with every experiment. The bridge is under construction, and what waits on the other side, a genuine scientific understanding of the physical basis of mind, is among the most profound destinations that the human drive to understand has ever aimed for. There is one more area that the mainstream discussion of quantum brain simulation consistently underweights, and it involves the organ that controls the brain rather than the brain itself. Not a higher organ, a chemical environment. The role of neuromodulation in shaping neural dynamics is so pervasive and so fundamental that no simulation of cognition can be considered complete without modeling it accurately. The brain does not run at a fixed operating point. Its computational properties change continuously depending on the levels of neuromodulatory chemicals like dopamine, serotonin, norepinephrine, and acetylcholine. These chemicals are released by small clusters of neurons in the brainstem and diffuse across large volumes of brain tissue, modulating the responsiveness of billions of neurons simultaneously. They set the tone of neural processing. They determine whether the brain is in a mode of focused exploitation of known solutions or open exploration of novel possibilities. They regulate the speed of learning, the threshold for action, the salience of reward, and the capacity for sustained attention. In terms of their physical mechanism, neuromodulators work by binding to receptors on the surface of neurons and triggering intracellular signaling cascades. These cascades involve a chain of molecular events: protein binding, conformational changes, enzyme activation that ultimately alter the electrical properties of the neuron, often through modification of ion channel function. Every step of this cascade involves quantum mechanical processes in proteins. The binding of a dopamine molecule to its receptor involves quantum mechanical recognition between molecular surfaces. The activation of the downstream signaling enzyme involves a conformational change driven by electron transfer. The modification of the ion channel involves a subtle rearrangement of protein structure that is exquisitely sensitive to the quantum state of the molecules involved. A quantum simulation of neuromodulatory signaling would be a scientific milestone in its own right. Many of the most important drugs in psychiatry work precisely by altering neuromodulatory signaling. Antidepressants modify serotonin levels. Antipsychotics target dopamine receptors. Stimulants enhance norepinephrine and dopamine signaling. We design these drugs by a combination of informed guesswork and clinical trial and error. The molecular details of how they alter neural dynamics, and therefore how they alter cognition and mood, are known only incompletely. A quantum simulation capable of modeling the full molecular cascade of neuromodulatory signaling would transform psychiatric drug development from art to engineering. The dopaminergic system in particular is intimately connected to some of the deepest questions in neuroscience and behavioral science. Dopamine is often described simply as the brain's pleasure chemical. This description is not quite right and misses what is more interesting. Contemporary neuroscience understands dopamine as primarily a reward prediction error signal. Dopamine neurons fire not when something good happens, but when something better than expected happens. If the brain predicts that pressing a lever will yield no reward and a reward appears, dopamine neurons fire strongly. If the brain predicts a reward and the reward arrives exactly as predicted, dopamine neurons barely fire. If the brain predicts a reward and it does not appear, dopamine neurons are suppressed below baseline. This reward prediction error signal is what drives learning. It teaches the brain what patterns of action lead to better outcomes than expected, so that those patterns can be reinforced. It is the engine of habit formation, skill acquisition, and motivated behavior. And it is exquisitely sensitive to the precise timing and magnitude of events. A change of a few milliseconds in the timing of a reward signal, or a change in the quantity of reward, smaller than can be detected consciously, alters the dopamine signal and changes what the brain learns. The quantum mechanical sensitivity of the molecular machinery driving dopaminergic neurons may be part of what allows this system to detect such fine-grained differences in the timing and magnitude of reward. A quantum simulation of the dopaminergic system would allow researchers to test this hypothesis directly. Does the quantum noise in the molecular machinery create variability in the reward prediction error signal that corresponds to the observed variability in human learning? Does disrupting specific quantum mechanical steps in the signaling cascade alter the precision of reward learning in ways that match the symptoms of conditions like addiction, depression, and schizophrenia? These are empirically meaningful questions. Answering them would advance our understanding of the neuroscience of mental illness far beyond what current experimental techniques can achieve. There is a feedback loop between neuromodulation and the quantum dynamics of neural tissue that deserves special attention. Neuromodulators alter the expression of genes inside neurons, changing which proteins the neuron produces over timescales of hours and days. These changes in protein composition alter the quantum mechanical properties of the neuron's molecular machinery. The neuron that exists tomorrow is physically different from the neuron that exists today, because the pattern of activity it experienced today has changed its gene expression. This is the molecular substrate of memory. Long-term memory storage involves the synthesis of new proteins at specific synapses, proteins that structurally modify the synaptic connection to make it more or less efficient. The molecular events that trigger protein synthesis at specific synapses are exquisitely localized and exquisitely sensitive. A synaptic connection that carries a significant pattern of correlated activity is marked for structural modification, while neighboring connections carrying random or uncorrelated activity are not. This selectivity, the ability of the synapse to distinguish meaningful correlated activity from background noise, may depend on quantum mechanical processes that classical models cannot capture. The NMDA receptor, a specific type of glutamate receptor, plays a central role in this process. NMDA receptors act as coincidence detectors. They open only when two conditions are met simultaneously. The presynaptic neuron must release glutamate, and the postsynaptic neuron must already be depolarized by other inputs. This AND gate property is what allows the synapse to detect correlated activity. When the NMDA receptor opens, it allows calcium to flow into the postsynaptic spine. The calcium signal triggers the intracellular cascade that ultimately leads to protein synthesis and synaptic strengthening. The biophysics of the NMDA receptor are known in some detail. The opening of the NMDA receptor requires not just the binding of glutamate, but also the removal of a magnesium ion that normally blocks the channel. This magnesium block is relieved only when the postsynaptic membrane is sufficiently depolarized. The timing of this event, the precise moment at which depolarization is sufficient to relieve the magnesium block while glutamate is still bound, is determined by the quantum mechanical dynamics of ion binding and channel conformation. A quantum simulation of NMDA receptor function would generate predictions about the precision of synaptic coincidence detection that could be tested against electrophysiological measurements. It would also generate predictions about how specific mutations in the NMDA receptor, many of which are associated with schizophrenia and autism spectrum disorder, alter the coincidence detection process. This level of molecular detail is precisely what distinguishes quantum simulation from classical simulation. A classical model of memory can capture the statistical relationship between neural activity patterns and synaptic strength changes. A quantum simulation captures the underlying physical process that generates those statistics. The difference between a statistical model and a physical simulation is not just mathematical, it is the difference between describing what happens and understanding why it happens. Understanding why things happen at the quantum mechanical level is what allows us to make predictions about novel situations, including the effects of drugs that have never been synthesized, mutations that have never been observed in a patient, or environmental conditions that have never been studied experimentally. A classical statistical model can only interpolate between known data points. A quantum simulation extrapolates from physical principles to novel regimes. This is the scientific value of getting the physics right. We have now surveyed the landscape of quantum brain simulation from multiple angles. The energy paradox that first signals classical inadequacy, the quantum biology that reveals the physical reality inside the neuron, the architecture of quantum computers that provides the right physical framework, the engineering breakthroughs that are making stable quantum computation practical, the applications in medicine, brain-computer interfaces, and consciousness research, and the deep molecular details of neuromodulation and memory that represent the ultimate frontier. Each angle reinforces the same conclusion, and that conclusion is not speculative. It is grounded in experimental results and physical reasoning that have been validated step by step over the past 2 decades. The human brain remains the most complex physical system we know of. It is more complex than any star, any weather system, any ecological network. Its complexity arises not from the number of its components, but from the richness of their interactions, and from the quantum mechanical precision with which those interactions are structured. We have been trying to simulate this system with tools that operate at a fundamentally different level of physical description. The mismatch has been visible for decades in every benchmark we have ever run, every simulation we have ever failed to scale. Quantum computing is the first technology that operates at the correct level of physical description to address this mismatch. It is not a silver bullet. It is not a technology that will arrive complete and ready to use. It is a research frontier with all of the uncertainty and difficulty that frontiers entail, but it is the right frontier. The physics says so, and the early results confirm it. The coming years will bring more results from quantum hardware platforms, more discoveries from quantum biology experiments, more demonstrations of quantum advantage for specific molecular simulation problems, and more refinements of the theoretical frameworks connecting quantum mechanics to neuroscience. Each of these developments will be a step toward the long-horizon goal of a real-time, physically faithful simulation of the human brain. When that goal is achieved, the scientific consequences will be profound. We will understand the brain as a physical system in a way that has never been possible before. We will be able to treat neurological and psychiatric diseases with a precision that is currently unimaginable. We will have brain-computer interfaces that are seamless extensions of biological cognition rather than clumsy prosthetics. And we will have confronted, with empirical tools rather than purely philosophical ones, the deepest question that science has yet approached: the question of what makes physical matter into an experiencing mind. None of these outcomes are guaranteed. Science never guarantees outcomes. What it guarantees is that serious, careful, physically grounded inquiry will generate knowledge. And the quantum brain simulation program is as serious, careful, and physically grounded as any scientific program currently underway. The brain is the universe's most intricate attempt to understand itself, and we are finally building the tools to help it succeed. Before we close, there is one more thread worth pulling, because it connects the physics of quantum computation to a question that is more personal than any of the others we have discussed. That question is about sleep. Every night, the human brain undergoes a process of dramatic reorganization. Synaptic connections that were active during the day are selectively pruned or strengthened. New proteins are synthesized at specific synapses. Waste products that accumulate during waking activity, including misfolded proteins like the beta amyloid associated with Alzheimer's disease, are cleared from the brain tissue through a system of fluid channels that is more active during sleep than during wakefulness. Memory traces formed during the day are consolidated through a process of replay, in which the patterns of activity that encoded a new experience are reactivated during slow-wave and rapid eye movement sleep. The neural dynamics of sleep are as complex and as important as the neural dynamics of waking cognition, and they are as poorly understood. The molecular mechanisms by which specific memories are selected for consolidation during sleep and others are allowed to decay are unknown in detail. The relationship between the oscillatory rhythms of sleeping brain activity, the slow waves of non-REM sleep, and the rapid oscillations of REM, and the molecular processes of synaptic modification that occur during these rhythms is known only in broad strokes. A quantum simulation of neural dynamics during sleep would be one of the most scientifically valuable experiments that could be run on such a platform. Sleep disturbances are associated with virtually every psychiatric and neurological condition. Chronic sleep deprivation is one of the most reliable ways to impair cognition and increase the risk of mental illness. The accumulation of amyloid during periods of insufficient sleep is one of the most compelling risk factors for Alzheimer's disease. Understanding the quantum mechanical details of what the brain is doing during sleep and why disrupting sleep disrupts health so severely could transform our ability to treat a vast range of conditions. It would also advance our understanding of consciousness from the negative space. Consciousness, whatever it is absent during dreamless sleep. The brain is still active during this phase, still running its molecular machinery, still clearing waste and consolidating memory, but the lights are off. Something that is present during waking and during REM dreaming is absent during dreamless sleep. If quantum simulation can identify what physical process, what pattern of quantum dynamics is present in the conscious state and absent in the dreamless sleep state, That identification would be among the most significant findings in the history of neuroscience. This is a concrete experimental question. It is not asking the abstract philosophical question of what consciousness is. It is asking the physically precise question of what changes between the waking state and the dreamless sleep state that could account for the difference in conscious experience. A quantum simulation that accurately models both states and identifies the physical difference would provide the strongest empirical constraint ever placed on theories of consciousness. The circadian rhythm that governs the sleep-wake cycle is itself regulated by molecular processes that are explicitly quantum mechanical. The core of the circadian clock is a transcription-translation feedback loop involving proteins called clock, BMAL1, PER, and CRY. The binding of these proteins to DNA and to each other, which drives the 24-hour oscillation of the clock, involves the same quantum mechanical molecular recognition that governs every protein-protein and protein-DNA interaction. Mutations in circadian clock genes cause severe circadian rhythm disorders, and these disorders are associated with increased risk of cancer, metabolic disease, psychiatric illness, and neurodegenerative disease. A quantum simulation of the molecular circadian clock would generate predictions about how specific mutations alter the timing and robustness of the oscillation. These predictions could be tested in cell cultures carrying the specific mutations, using fluorescent reporters of clock gene expression to track the oscillation in real time. The combination of quantum simulation and single-cell experimental measurement would provide a feedback loop capable of identifying the quantum mechanical details that make the circadian clock accurate to within minutes over a 24-hour cycle. The accuracy of the circadian clock is itself a remarkable physical phenomenon. A molecular oscillator involving a small number of protein molecules oscillating through a transcription-translation cycle that takes approximately 24 hours manages to keep time with a precision that the most accurate classical mechanical clocks took decades of engineering, refinement to achieve. The molecular noise that would be expected to cause drift in such a small molecular system is somehow suppressed. Whether quantum coherence plays a role in this noise suppression is an open question that a quantum simulation could address. We keep returning to the same theme because the data keeps pointing in the same direction. Every biological system we look at closely enough reveals quantum mechanical features that contribute to its function. The precision, efficiency, and flexibility of biological systems cannot be fully explained by classical chemistry. Quantum mechanics is the missing layer of physical description, and its absence from our computational models of biology, including the brain, is responsible for the gap between what our models predict and what our experiments observe. The closing of that gap is what the quantum brain simulation program is about. Not just the brain, not just medicine, the entire enterprise of understanding living systems at the level of their fundamental physics. This is the scientific frontier of the coming decades, and it is the frontier where the most significant discoveries about the nature of life, mind, and matter will be made. We are living in a remarkable moment. The combination of quantum hardware, quantum algorithms, experimental techniques in quantum biology, and theoretical advances in neuroscience has created an opportunity that did not exist a generation ago. The scientific and technological pieces are coming together in a way that makes previously impossible investigations possible. The questions have always been there. The tools are becoming real. The energy gap between the brain and the supercomputer was always a signal. It was nature's way of telling us that we were looking in the wrong direction. Quantum mechanics is the right direction. The brain knew this all along because it had no choice. It was built from physics, and physics is quantum. We are finally catching up. For everyone watching this story unfold, whether as a scientist working at its frontier or as someone trying to understand what it means, the message is the same. This is real. The physics is sound. The biology is consistent. The engineering is advancing. And what is being reached for, a genuine physical understanding of the mind, is among the most important goals that science has ever pursued. Pay attention to what comes next. It will be worth watching.